and gentlemen, we are there. Lecture 4. Sort of a bonus lecture. We planned only for 3. I sort of, in some sense, used some of its bonus feature already in the previous one, so it's still mostly core material. Just to, there's the, plug in one more thing with the design system. Remind you of the roadmap that we had, describing data. We're done with that for now. And then we describe what we expect, basically the theory, putting the theory in terms of what we expect in data. So translating your standard model into a probability density function of seeing some bump in your data, this kind of thing. And then comparing that with what you see in data. And we have done part of that. We have done a little bit of probability distributions, even though we did the binomial and Poisson, for example. We did the central limit theorem, my favorite theorem ever, and we did fitting. Today we do probability density functions, so they're basically a missing bit. We've actually already done a bit of that. The Gaussian we discussed is a probability density function. And we do more fitting, and we do Monte Carlo simulation. And then we see where we are, I think. We'll probably be exhausted and done, but I do have bonus material for those who are inexhaustible. So, this is what we did yesterday. We fitted, we did a few other things, but at the end, we fitted a distribution of data with a function. That function was this exponential decay rate, and the parameter we fitted was this red one, tau. And you did this by guessing values, guessing very nicely. I'm grateful to every single guess, but most grateful for the first one who broke the ice. Thank you very much. And it was a sensible guess as well, actually. And we found that the best guess, the best estimate given the data is 1.65. And then we even managed to estimate the uncertainty on this value. And the uncertainty on this value is, roughly speaking, the typical distance of this value from the truth. Roughly speaking. It has also a fairly precise meaning. It means that in the interval of 1.65 plus minus this uncertainty, if I repeated this experiment again and again and again and again, then in 68% of the cases, I should have a true value within my interval. That is obviously precisely. Alright. And the thing that we minimized was this function that was a chi-squared, and that in a sense is a distance between the function and the measured values. So this is what the function predicts I should find in my histogram bin. This is histogram bin number I, and this is what I find. The number of events I find in histogram bin number I, and that sigma here actually have its own index. I don't know what happened to that. You calculate that bit by bit. And we square all of this and we add them up. That's a chi-squared. And we minimize this kind of distance between the data and the theory. Now, I can minimize this distance for any data and any theory. So what this doesn't tell me, it tells me what my best theory parameter is, but it doesn't tell me whether I've got the right theory and whether the theory is compatible with the data. And we've had this look at how a good fit looks like and a bad fit looks like. This clearly looks like a bad fit. This looks like a good fit. I can minimize my chi-squared for both of these. So the fact that I find a minimum, I can estimate an uncertainty for my parameter, etc. The fact that I find a minimum and an uncertainty doesn't tell me that I actually chose a sensible parameterization. But there's a way of doing that to estimate the fit quality, if you like. I call it badness of fit because that's in a sense what most people would say goodness of fit. But in a way, what we estimate is really closer to the badness of it, if you like. But you'll see what I mean in a moment. So this is our definition of the chi-squared, now with the important index I restored. Given this definition, and I have n bins, what is a typical value you would expect if you have a decent fit? The numbers that we have here are, I don't know, there are not that many numbers. There are small n's, f, sigmas, big N, I. Any one of those, or 10 times that, pi, 0, 1. Any guess? Maybe I give you, what, sorry? 0. Now,
0.
That would be the case if indeed my fit went through each data point exactly. Now, even if my theory is correctly describes the underlying distribution that my data come from, I don't expect my line, so it's a good fit, to go through every single data point. It's quite unlikely because the line basically tells you what I should see on average in each bin if I repeated the thing infinitely often. But in every measurement I make, I will find actually there are statistical fluctuations. And actually, the statistical fluctuations in each bin, they're going to be Poisson distributions around the value that I expect. So I expect n events in this bin, what I get is n plus minus square root n. So that's what, so I expect some wiggle. And remembering that the variance, the square of the standard deviation, this is the standard deviation, the square of the standard deviation is the variance, and that is basically this thing, the expectation value of this thing. That is the variance, right? So the expectation value of the numerator is what I have in the denominator if I got my uncertainties right. Given this information, I give it one more shot. What do you expect for each of these terms on average to get, given that the expectation value of the numerator is the denominator? Yeah, 1 for each term. So we add up n, on average we should get about n for our chi-squared. Very good. And so often put in this form, so divide the chi-squared by the number of bins, you should get about 1. That is step 1. We complicate things a little bit now. And the way I complicate things is, I think I'll complicate things here. Let me complicate things here for you. Because life would not be too easy after all, right? There it is. So let's say I have this data point here. I don't care about the errors, and then I have this data point, and maybe that's it. And then I have a theory, and my theory is a simple line like this. But now I add a fit parameter to this. So at the moment this is just a theory without fit parameters. And I compare it to the blue points to my orange theory. Now I add a fit parameter, it means I can wiggle this. So, and if I have two fit parameters, one for the overall height maybe and one for the slope, then I can actually draw right through the points. So imagine you have n data points. If you get a polynomial of order n, you can draw your line exactly through all these data points. That doesn't mean necessarily it's very meaningful, but you can do that. So this additional freedom I have by adjusting parameters, that will reduce my chi-squared. The more parameters I have, the smaller my chi-squared will be. And So this is why instead of dividing by n, we instead of dividing by n, we divide by the number of bins minus the number of fit parameters. That takes into account this additional wiggle room I get when I can adjust my function. And that is called the chi-squared per degree of freedom. That's about 1. Now what happens if I don't get 1? How concerned should I be? So this is a good rule of thumb. Let's be more precise, because we want to be precise in our statistics. We can calculate, there's a probability density function that tells us, and we learned in the second what probability density functions actually are, but we know the Gaussian already. This is another one that tells us the probability to get a density to get a certain chi-squared given a number of degrees of freedom. The one thing to remember about probability density functions: never evaluate. Do so at your peril, but if you evaluate the value at one point, it usually doesn't mean anything. You always want to integrate them. If you answer a question that involves a probability density function, and your answer involves just the value at a given point, it probably is the wrong answer. Except if your teacher asks you for some reason what is the value of this point. Physics meaningful answers are integrals, and here what we integrate over is, let's say we have our measurement, and we have 10 degrees of freedom, so this is how this probability curve looks like for 10 degrees of freedom, or 4. And we find a chi-squared of 16. Then we ask ourselves, to estimate how bad this is, we ask ourselves, how likely am I to get a fit this bad or worse? And the or worse is important, so we integrate from 16 all the way to infinity. That tells me how likely am I to get a fit this bad or worse, under the assumption that my function actually describes the data. And if this number is very small, that's an indication that the fit is not very good. All right. That concludes basically yesterday's lecture by adding to our ability to estimate the best parameter of our model also a way of evaluating whether our model is actually a decent fit. The large chi-squareds are worrying, basically, and we can evaluate how worrying by calculating. This thing is actually typically referred to as a p-value. Yes, please.
Do you see any correlation between the parameters? Do you fit and overfitting? So what is the limit what could be an ultimate upper limit on the numbers of parameters that we fit to the data?
That's an interesting question. I think it depends on the situation. If we have a solid theory behind it, you're not going to overfit by definition in a sense, because you know what your theory should be. You just have the theory parameters, and those you can vary. But this is, in practice, very unlikely, because typically you have a theory what the mass of the Higgs boson is, but you don't have a very good theory about how the width of this is described due to detector resolution effects, and that dominates the width that you see in there. And that can be described by very complicated functions. At LHC we tend to use not just one Gaussian, but 2 different ones, plus tail parameters, plus all sorts of things. So yes, you can over-parameterize things. I think I don't have a hard and fast rule for that.
And then in the end, one can calculate or quote the fit uncertainty due to the choice of the fitting function, just to limitize the various parameters that one can have.
Yes, one thing, if you're really worried about this, there are techniques such as lasso, etc., that do tell you which parameters matter and which ones don't. I think they tend to require a certain degree of human supervision. They don't work out of the box there. They give you some guidance, but I've had mixed experience with lasso, for example. There are apparently better ones than lasso, I forgot the names. But these are interesting ways of catching out parameters that actually don't really help anymore in the fit. I would go by eye, by the way. If I see something very wiggly going through all the points, I probably have done an overfitting. I want to have a smooth curve. A curve that's much smoother. It's a qualitative statement, but I want a curve that's much smoother than the statistical fluctuations in my data set. That would be my rule of thumb.
Yeah, because fitting by an eye when it comes to the histogram is sometimes very tricky. Because the data points which are unbinned, it's pretty simple. Okay, it's a parabolic or straight line. But when it comes to the binned data, then it's really not describing.
I mean, the chi-square distribution is still fine. I mean, and the minimization still gives you this parabola, so that's okay. I think that's the only thing with binned data. I don't want to elaborate too much, but the only problem with binned data that you have is that typically you approximate the theory by the PDF at the center of the bin times something that depends on the total amount of data you have. Basically, when it's center of the bin times bin width is how you approximate the integral of the probability density function across the bin. And that works for small bins. If you have very large bins, you have to start calculating integrals properly rather than taking the value in the middle.
Thank you.
All right. Now, I talked about all this integration business and probability density functions. Let's now introduce these properly and formally. It starts with a question again. So I have 100 strings between 10 and 12 centimeters, and I measure their length precisely. How many are 11 centimeters long? I had a few of you have asked this question, but during lunch or something, and I think a few days ago. Any guesses? Well, remember, the answers for these things are typically either pi, 1, or 0. So pick one of those three. Which do you think is the most likely one? One? No? Okay. Either pi or 0. So which one? It's 0. The answer is 0. The probability to find one. Oops. I've left the explanation out. The probability to find a string between 10.99 centimeters and 11.01 centimeters, that is not 0. But I can make my interval shorter, so there's still going to be a probability to find a string that is between 10.999999999 centimeters and 11.000000000001 centimeters. But once I start specifying all infinite digits of these real numbers, the probability goes to 0. And that is a feature, not of statistics, or I've had people explain it with quantum fluctuations, nothing to do with that. It's a fundamental feature of how the real numbers lie densely on the real axis. That is the reason why, because you have basically infinitely many real numbers next to any infinitely small distance around any real number. Fractions will do the same thing here in this case, probably still. So the probability to get any single value, quite mind-boggling because you do get values in the end, right? But the probability to get any one of them is 0. So how do we, for those who find this a bit difficult to imagine, think of concepts like mass densities. You have a body, and you define for every point in this body a mass density. We can do that. But the mass of this point is 0. The mass of the point is 0 because the point has no extension. It has 0 volume. But if you want to have something meaningful, then you integrate over some part of that body, and that gives you the mass of that part of the body. And you integrate over this mass density over part of the body. That's what we do with probability density functions that describe continuous variables. We describe a density of probability, and then the probability is the integral over a certain finite region. So that is the magic of probability density functions. So the important bit, and here I hate my notations, I have to admit, I should have changed it. This and this, these are not the same symbol. Apologies, I should have. Usually, and I haven't fixed it in this slide, I make this a small p or something like that, or something different. So this is a probability density function, and this then gives you an actual probability. on the left-hand side. In practice, for example, if you want to have the probability that an event lies in a histogram bin, these bins are often quite small, then you can approximate it by taking the value in the middle of the bin times the bin width. But this is meant to be this integral, and it's usually a good approximation of this integral, but only for small bin widths. And this Gaussian that we discussed earlier is such a probability density function. And it is this thing that's why it's nearly always meaningless to calculate a probability density function at one single point, because it doesn't give you an answer that means anything physically. It only means something if you integrate it or something. Quite important. So, but in many ways, probability density functions behave like probabilities. We can calculate, if we want to normalize, for example, the probability that something happens is 1. We can calculate expectation values of a parameter or something else. This could be, for example, x. This f of x could be x squared, and we can calculate a variance, which is the expected, variance of that our data would give us if we sample according to this probability density function. So, in this sense, they're very similar to probabilities, but they're there's actually two senses in which they are not very similar. One of the things that sorry for flicking around, but if I look at this expression, this is a probability, then this thing here, the probability has no units. The probability density function always does. It has to have units, because if this is in meters, then this thing has to be in 1/meters in order to give something without units. So that's one of the ways in which probability density functions are different from probabilities. They have units, and therefore they also quite depend on in what kind of parameters and what units or whatever you measure things. And that can have dramatic consequences. So if I say this is a probability density function, then I want to change parameters. One example could be that an example I will have on the next slide is I could measure the diameter of a pipe, but I might be more interested in another parameter that is the cross-section of that pipe. And I have a very weird factory that produces pipes of random diameter or random cross-section, and if I might want to change from one parameter. I know the probability to have some diameter, and I want to calculate the cross-section instead. The probability density function then changes. So the probabilities, they don't change. They should be independent of my choice of parameter. So P of y dy is the same as P of x dx. These are my probabilities, differential probabilities. But that means that P of y is now P of x times dx by dy. And the final little thing, this could be positive or negative. We don't like negative probability density functions, so we only take the magnitude of this. And that can have dramatic effects on how these things look like. So I have got an example here. This is my pipe example. I didn't take the cross-section, I take the side length of the pipe as x, and the cross-section of the pipe is y. And I have a really weird factory that very randomly produces pipes between a side length of 0 and 10 whatever units, randomly, a flat distribution. It looks like this. Beyond this, it's 0. Y is 0.1. Who's still awake? Who's asleep? Who's still here? There's somebody here. I'm so glad. So if you look at this, and I want a flat distribution between 0 and 10, and then 0 outside, why does this flat distribution have to have a value at 0.1 where it's not 0? There's a reason. Technically, at 0.1 inverse length units.
The area under the curve should be 1 and...
Indeed, the area under the curve, this gentleman has it. The area under the curve should be 1 because we want normalized probability density functions. So if I integrate over the entire function, I want 1. The area under this curve is 10 times this, 10 times 0.1 is 1. So that's why it has to be 0.1. And if this were only 5 units wide, then this would be 0.2. Right. Now I change my variables, so y is x squared, y is this area, and I go through this entire calculation. So p of y dy is p of x dx, and this manipulation we've already seen. So all I need to calculate is now dx by dy, and dx by dy is 1 divided by square root by 2 times square root y. So and I put then p of x in, p of x is 0.1. So this is my new probability density function. It's very different from the previous one. The previous one was flat between these values, and the value was 0.1 and 0 elsewhere. This one is not bounded. It goes all the way to infinity. It has a very different shape. You can do anything, actually, well, anything. You can change the shape of these things quite a lot, and you can use this. The computer typically generates something like this between 0 and 1. If you find a good variable transformation, you can generate anything, well, more or less. It's not always easy to find the right one, but for example, a Bragg-Wigner or an exponential you can generate in that way, just using a parameter transformation from a flat distribution. All right, so everybody happy with PDFs? Because we're going to use them now. Yes, please.
So what if we have a parameter that depends on multiple variables?
Then you have a multidimensional PDF. That is completely fine. Then you don't integrate over 1 dimension anymore, but over 2 or 3 or 4 or something like that. That is completely analogous. I've not treated it here, but that is okay. Multidimensional PDFs are fine. You find them in quantum mechanics all the time, in a way, although there's a slight pitch in the meaning. But yeah. So now let's use these PDFs in order to do fitting. We did chi-square fitting just a day ago, and this is used for bin data, and it has one weakness. This weakness is not too bad. I mean, chi-square fitting is not too bad, but the weakness, the primary weakness is that by putting data into bins, you lose information, because you don't know anymore where in this bin the data point was. And that can be of quite some disadvantage if you don't have all that much data, if you want to get the maximum information out of it. That motivates looking for unbinned methods. And the unbinned method that I'm going to introduce to you is the best, which can actually be proven by some metric it is the best, and that is a likelihood. Now, the likelihood, we are familiar now with the idea of a PDF that describes the probability density to see a certain outcome. We multiply all of these probabilities or probability densities together for all my data points. Think again of our lifetime fit. We take data, and for each data point, I calculate what's the probability density given my model to see, find the data point at decay at time t, I. Now multiply that together. What this gives me is actually a probability, or probability density, strictly speaking. And it is a probability density to see my data given my model. I reinterpret this. I mean, it is still the same thing. I've not done anything to it, but I reinterpret it as a function of my parameter rather than a function of the data. And say this I call likelihood. So the probability to see the data given my parameter, that's seen as a function of the parameter. It's called the likelihood. And I maximize this. I wiggle my parameter until that's maximum. Okay. So in practice, dealing with these very long products is painful. It's easier to calculate the logarithms and add them up because the logarithm is a strictly monotonous function. It has the same maximum or minimum as likelihood, so we can use this. We can just maximize that instead. That is easier. All right. So we've already had this. Just a quick reminder that this property in this context is crucial to normalization, and I will show you that in our first likelihood fit. All right? All right. So I'm about, I need probably another 20 minutes, so we'll be done by 4. I hope that's okay. Okay, so now do we do this? I think I want to do the likelihood fit first, then we worry about the uncertainties on it. So we'll do a likelihood fit. Now, somewhat different to how we did it for the chi-square fit. This time I'm not going to use a program to do this. I'm going to do it, very good. I'm going to do it by hand. This is not a feature of the likelihood fit that is easier to do by hand or say. I just thought you should maybe see it once, how this is done. So we want to fit, I think I want blue in my color. We want to fit this. That was my, and I have a bunch of data, and these are my data. This is n data points, and I want to find out, given those data, what is my best value, my best guess for tau. So my log likelihood, that is the sum, the logarithm of the product and the sum of the logarithm of this thing, which is 1 divided by tau, e to the minus t tau. And I need to give more space because, of course, I need to give things an index, t. The t, these are my data points. I get an index, and then I have this. So this is my likelihood. How do you find the maximum of this? You differentiate it and set this to 0. So we have, we say 0 is, no, well, I think I can say, yeah, you're okay with my little trick because it saves me a line, and you can see more things at once. So, okay, so this is then so minus logarithm of tau minus the logarithm of e to the t blah blah blah. That's t I divided by tau. As in the past, I often make mistakes. Please shout if I do. Nearly made a sign error earlier. So do watch me. That thing is, we do the first differentiation. This one here. That is then minus 1 divided by, we need the sum sign. Minus 1 divided by tau, right? And then this is plus t I tau squared. Is this correct? I see you nodding. Okay. If it's not correct, we're going to stay here forever because if I make a mistake now, it's going to turn into a huge mess later on, and we'll take forever to find out. So do watch this. So we sum over I, and then so we have 0 is the sum over all the i's going from 1 to n minus 1 divided by tau plus the sum over di tau squared I 1 going to n. Now what is this? Easy peasy, I add tau plus 1 over tau plus 1 over tau plus 1 over tau n times. It's n divided by tau. Thank you. I just heard this somewhere. I hope it was not me just dreaming. So this is minus n divided by tau. Then we have this, and that is plus. There we can't do much. We can take the tau squared outside. 1 over tau squared. Yeah. Okay? Now I'm going to solve this for tau squared, for tau, not for tau squared. And I'm going to do this by multiplying this entire thing by tau squared. So I have minus n times tau plus this sum. No, I'm getting sloppy and sloppy with my drawing. That's 0. And then if I put the well, this is not becoming obvious, I hope. Right? Do you see what it is? It is the mean. Hooray! Right. So this is quite a, I think it's quite a satisfying result, and we did it by hand. Nearly all fits that you do, you will not be able to do by hand like this because it's too complicated. You'll have some detector effects to take into account. Your likelihood will quickly become too messy, but it's good to have seen once how this works and that it does work actually. I find it very satisfying anyway. All right. Now, let's move on to, I think I'm going to sort of only mention how you do the uncertainties on this. Yeah, one last thing actually. That's just follow.
We can't see.
Yes, we can't see it. That's true. That's true. That's bad. Where are we? There. Just follow the fate of this. This is a normalization term. This term was only there. It doesn't change the shape, but just there to normalize my PDF to make sure the integral is 1. If I hadn't had this guy here, the entire thing would have given me a completely different and wrong result. So the normalization really matters. Don't forget about that. It'll be a fitful. It's a classic mistake in the likelihood fit to mess up your normalization and then you get the wrong result. Because normalization is not always easy to calculate. It's impossible.
A question to them would be if I take instead of exponential decaying function, I mean just take the Gaussian function, what would be the mean at the end of this one?
So I've done that. You can do the Gaussian also analytically, by the way. Turns out to be the same, it's also the mean. But not, that isn't the case for all functions, but for the Gaussian it's the same. And the standard deviation is a standard deviation, turns out. Yeah. But the Gaussian you can do analytically by hand. Good exercise, find out. Regarding uncertainties, the explanation I give there is just too end wavy. Forget about the explanation, just accept it that you can get the uncertainty on the fit by going moving outwards from the best value, from the maximum of likelihood, until it changes by 1/2. And it has to do at the end with this thing being, for large numbers of events, a parabola, that's a log likelihood, and that has to do with the fact that the likelihood becomes near the maximum Gaussian. And that has to do with the central limit theorem, but it's all a bit vague. Alternatively, you can get this value out here, which is basically this is the uncertainty, by calculating the second derivative and then taking the inverse. So the uncertainty and also we got it from the curvature. And we could do this now, but I don't want to spend the time. But we could do this for the lifetime fit. It's not that hard actually. But because we are already running out of time again, I'm not going to do it. If it's not Gaussian, the rule still works. You go out until the likelihood changes, the log likelihood changes by half. And that means that you can get asymmetric uncertainties. Again, with the warning that I did last time, because it's the same process except for going to 1 rather than a half as for the chi-squared. If you can avoid asymmetric uncertainties, do. So if they're only a little bit asymmetric, just have them the same on both sides. It's otherwise very painful for error propagation. One of the most important things that often misunderstood is that the likelihood it gives you how likely you are to get the data given the model. It doesn't give you how good the model is at all. So this is a toy example that I did for my graduate students. These are two likelihood fits to the same likelihood, the same PDF, the same likelihood to sensible data, this is some B oscillations stuff, and to complete garbage data. The likelihood for the garbage data is bigger by 4 units than the likelihood to the sensible data. And you can see by either of this rubbish, but the likelihood doesn't tell you that. So don't take the absolute likelihood value as anything of any meaning. There's no case in which the absolute likelihood value has a meaning. There are cases where log likelihood differences have meanings, but the bare value by itself has none. And certainly doesn't tell you whether you've got a good fit or not. All right. And again, I'm going to skip something because I want to be done by 4. One fun thing to do, no, I'm not going to skip it. I'm going to do it a bit quicker. One fun thing to do is a binned likelihood fit. So the chi-squared fit came more or less out of the blue. I told you this is how we measure the distance between the function and the data, and we came up with a chi-squared. You can start from a likelihood fit and calculate the probability to find n events, given that you expect f events. You calculate the probability to find n events in your histogram bin, and that is going to be a Poisson distribution. I always imagine I'm a little frog, sits in the histogram bin, so things come, events come, and every now and again, poof, one ends in my bin. So that's very similar to this flashes of lightning kind of situation. So the fluctuations in the histogram bin around the average value are governed by Poisson fluctuations. That's why error bars are usually drawn as the square root of the number of events in the bin. So we use this then. So the lambda thing is the expected value, and n is what we measure. And then we go through some math, blah, 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 and we end up with this. And we take the logarithm of our likelihood, we basically get this thing, and that looks very much like a chi-squared, and that's what it is. It is a chi-squared. The sigma here, that's just the uncertainty on the number of events in each bin. That's square root n. And that means that I can derive the chi-square fit from the likelihood. Yes?
Is this actually correct? So I would say f shouldn't it be integral with the bin of the function?
You should have the integral here. Also for chi-square fit, you should have the integral. The integral is usually then approximated by the value in the middle times the bin width, and the bin width factors out, and you forget about that.
No, it very much doesn't factor out, right? Because as you make the bin smaller, your statistics get smaller, right?
That doesn't matter. I mean, that yes, but you still add up just all the bins. I mean, as long as you have the same bin width, you get the sum times the delta x, right? It will affect your fit because the statistics per bin gets smaller, etc. All that doesn't matter. The critical step here, though, and that's where the statistics matter, is that here, in order to get from my likelihood fit, from my bin likelihood fit to the chi-squared fit, I approximate my Poisson with a Gaussian. That gives me this characteristic likelihood term, the chi-squared term, and that means chi-squared fit will only work if you have enough bins in your enough events in your bin that the Gaussian approximation is good. And that's quite important because that's a source of many biases. So if you have less than 10 events in your bin, you need to think about merging bins and things like that. So rule of thumb, chi-square fit with bins, especially with many bins with less than 10 events in them, is an unreliable business. All right. So that's what I just said. So if you have that situation, you can merge bins. So just have bigger bins. You can do bin likelihood fit that is insensitive to this kind of thing, or you do non-bin fit altogether. That can be quite a good thing as well. This is the royal solution to this, but it's also often a bit harder.
Since we are not sure where the point in the bin is lying, why can't we merge all the bins together in just
you can do. And each time, the wider your bin, the less information. So you will find that the uncertainty on your fit increases as you do so. You can do it, of course. But if you merge all of them, then all you fit is the total number of events. That you know to start with. That probably doesn't contain any information. But I could have done my lifetime fit with 2 bins, I'm sure. It just would not have been the optimal use of information. Yes, please.
Yeah, so with the likelihood estimation, I'm going to ask the basic optimization question. Like, what if there are more than one maxima in likelihood?
Well, then you're in trouble. We ignored this a little bit, but it might be. I mean, the shape of this likelihood can be quite complicated. You can have several maxima. You can have a clear global maximum and smaller ones. You'll have to deal with it. The typical situation is you have one global maximum and a few, and possibly, if it's a complicated fit, for our examples we wouldn't have a problem there, but for complicated fit you might have local maxima. I think the thing to do is to repeat your fit many times with different starting values and then see where it lands in which maximum, because your fit can easily get stuck in a local maximum, but if you start at a different point it might get stuck in another one, and then take the overall global maximum that you get.
Similar to what we do in gradient descent and deep learning, right? Something similar when we are stuck in a global, like local region.
The problem, I mean, that's what your fitter does. It will do exactly this. It will do gradient descent or some version of that. And then you might be stuck in a maximum, yes.
Or trying to group the correlated and uncorrelated uncertainty together to smooth the fitting procedures.
Yes, but you might end up just having really these multiple maxima. It happens. It doesn't always happen. A good thing to do, if you're in trouble with your fit, by the way, draw the likelihood curve. Draw the entire thing over a sensible range, and then you see whether you have multiple maxima or minima. Now, I'm sorry, I'm overrunning slightly. I mean, not relative to the starting point of time, but relative to where I wanted to end. So that's the final bit of this, and it's an appeal to you to please do this. Test your fit. So there are complications. First of all, you can have made a mistake. That's easily done, and most of the time you will make a mistake if you write your own fitter. And so you have to find those and debug this. And then you can have complicated likelihoods that give you the wrong answer for a perfectly good reason. Maybe there are multiple maxima, or your fitter will fit the negative log likelihood and get stuck in minima. But that doesn't matter. That's the same thing. So to investigate this, having a test of your fit is a good thing. And the way to test your fit is simulating lots of data samples using simulated events, using the Monte Carlo method. And that's a final topic, and it's going to take me another 10 minutes, I think, or 15, with your help. 15 probably. So each data set basically represents one experiment, one LHC or whatever. And you fit your data, and then you calculate the this value, the fit result, minus the true value divided by the error estimate. And the true value is something you know because you wrote the simulation, and in this simulation, you're all powerful and all knowing. In nature, in reality, we don't know this, but in the fit, we do. And then you put that into a histogram, and for a good fit, the histogram will be centered at 0, and for good error estimates, it will also have width 1. So you test two things at once, which is quite nice. You fit whether the central values come out right, and whether the uncertainties come out right. And this is an example where things went badly, went wrong, and were then fixed. Here sigma was 1.4. Always suspicious at square root 2. It was a situation where events were duplicated. So the fitter thought it had twice as many events as it did information, basically. And so the uncertainties were bigger. All right. So, any questions regarding this? Okay, let's do the Monte Carlo simulation. So this works like this. We want to simulate events according, and we want to do it simply. I mean, there are Monte Carlo simulations, essential detector simulation by CMS, etc. These are very valuable, but that's not what I mean. I want a simple, fast simulation that generates data according to the probability density function that you assume in your fit. So it's a closure check whether your fit is self-consistent. Okay? That's what you want to do. And so this is my example of a random function I want to generate data according to. And the way I do this in a very generic and way that always works, it's not the most efficient, but it always works, is I enclose it in a box. I have to make sure that the upper line of the box is above the maximum of the function. And then I shoot at it randomly, and I accept the events below, and I reject the events above my function. And that means at every point here, the probability that an event gets accepted is exactly proportional to the height of that function. And that's what I want. And that's how simple Monte Carlo simulation works. This is the root code to do this. You generate two random numbers, one in the x and then one in the y direction. And you can also use that for integration because the fraction of accepted events is proportional to the area underneath the function. So if I know the area of the box, which is easy usually, I also know the area of the function, and that gives me the integral. This is, for one-dimensional integrals, probably the most inefficient way of calculating an integral. It turns out, for multi-dimensional integrals, so beyond 3 or 4 dimensions, this is actually one of the most efficient ways of doing it. A bit surprising because it involves random numbers, but it works very well. Okay, so let's do our own Monte Carlo. So we do now a Monte Carlo integration, and our aim is to calculate pi. So how do I want to calculate pi? So the plan is. Oops, I'm lucky. No. The plan is, so this is oops, that's a bit too fat, huh? No. The plan is to do something like this, x, y, and then this is a quarter of a circle, and we do Monte Carlo integration is that thing, and that should tell us what pi is, because if we say this is 1, then the area is pi squared over 4. Right? Pi squared over 4? It's a quarter of a circle. The area of a circle is pi squared. Pi r squared? No, pi r squared. So it's pi over 4. Thank you. Not pi squared. Pi over 4, not pi squared over 4. Pi over 4. And can I ask you to create a missile of some kind? Something you can throw. Piece of paper works, but tightly. If you still have my dice, this would be a way of giving them back to me. Although be careful, they're quite hard. Don't throw them too much. So your task would be let's see, thanks to, by the way, the several people actually who might need helped me draw this and make this. So this is my more or less a square, I think, and I need a pen, and I need long enough, yes, and I need a helper. Is anybody willing to? Yes, please. Your task is to just hold this at this point, and then you can see how this. You will see how my logic is. So. Oops. Yeah. That's enough. All right, and then draw a line here. This is a straight line. If you don't see a straight line, take your glasses off and it'll be straight. All right. So, look. Oh, yes, maybe. That's also possible. Yes. So, have you got a piece of paper or something else to throw? The more, the better. Throw several things. So, give a second. Throw stuff. Go ahead. I'll throw something.
Try come here. All of you just come here, okay? Instead of, it will not go into it. At least we want to try.
Yeah, feel free to come a bit closer.
Come here and throw over this one. ऐसे करके यार इधर आ जाओ मेहंदी नहीं लेंदी इतने आ रहे हो मेहंदी लेंदी तो लदा गल इतने आ रहे हो हाँ कॉइन्स थ्रो कर नहीं इतने इन्होंने देने नहीं दे मोबाइल देखिए उसने अपना वो हेडफोन थ्रो कर दिया आपने थ्रो कर दिया
I think I can see I hope for a few more things being thrown.
कसम से कोई काम एक्सपेरिमेंट भी ना करना है ऐन सटना है क्या मसला है
So just for those that are this is where we are at the moment with this. So I think we need a bit higher statistics. So yeah, feel free to give things another go. All right. We're getting there. Yeah, I've got this is how I augment my pen selection. That's great. So excellent. Okay, so let's. Okay, so this looks quite good. I think this is probably enough. I need 2 counting officers. It's a very highly responsible job. Counting officer number 1 and counting officer number 2. You have the task to do the same thing. Count how many we have in total, and how many are inside and how many are outside. And if you don't agree on the number, I don't know, take the average or something. But you see the highly All right. So we have a result.
Out of second, 7. And outside of equal to.
Yeah, you need to bear with me. I need to write this down. Of course, I will not remember it. You have to remember it now for me for a moment. So we have inside. You have 21.
Inside the circle.
Okay. So 21 and outside
7.
7. So the total is 28. Thank you very much. So let's see what is pi. We said that so the ratio of the total, so this is area 1, so the ratio of the total divided by the box is pi over 4, and that should be 21, or proportional, yeah, 21 divided by 28. I couldn't be more grateful. It's very rare that we have numbers that that have a common divisor. So this is 3 quarters. Oh, sorry about that. I don't know why this is. Well, it's still there. 3 quarters. Okay, so that's good. That means pi is 3, as they believe in Kansas, I believe. So what's the uncertainty on this? That's clearly the question, right? That's the important question. And that's not an easy question. What kind of probability distribution would you use to describe the situation we have there, where we have, just to push you in the right direction, we have a number of balls and other missiles that are either inside or outside the circle. Binomial wins or so. It's not bad in a sense, but here I think binomial works better. We sort of discard anything that didn't hit the square. Actually, in this case, we pushed everything inside, which might be a bit naughty, but we discard everything outside the square, and then given that it ended up on the square, so the number of things in the square, n is now 28, it's the total number of trials, and then the question is inside or outside, there's 2 possible outcomes. So the uncertainty on what though? The uncertainty on is going to be on this number. That's what we're going to calculate the uncertainty for. So this is the number of successes, if you like, after 28 trials, is 21. So sigma numerator, if you like, that is square root n times p times 1 minus p. Now that is square root n. N we know, n is 28, but we don't know p really. We just, well, we don't know the underlying p. We have to get the p that we measure as our best guess. The probability to end inside the circle is 3/4 as our best guess, right? That's what we measure. So we just put our best guess instead of the absolute theory truth, times 1 minus p. 1 minus 3/4 is 1/4. We were really super lucky that these are so easy numbers. So that means that we have square root of 16. First of all, we calculate this is 7,
84.
and that's the other way. And then this is 7 times 3 is 21 quarters, right? Yeah?
Yes.
Yeah, okay, good. So, what is the square root of 21 quarters? It's not square root of 5, and that is 2 point something. Let's not overdo it with the working things out in our head. Let's just ask our computer friend to do this, and it's 2.3. Okay, so that's 2.3. Yeah, very good. So I'm trying to keep everything here on this thing. So the uncertainty on this number here is 2.3. So we have pi quarters is 21 plus minus 2.3 divided by 28. So the uncertainty, sigma on pi quarters, that is 2.3 divided by 28.
Screen.
Sorry?
Oh,
how annoying. Better?
yeah.
So, the uncertainty on my pi quarters is 2.3 only, divided by 28, and that is roughly, it's less than 0.1, huh? That's 0.08. And that is fine. So, and then the uncertainty on pi, that is this times 4, right? Is 0.32. So our final result, let's do this yet another color. Pi is 3.0 plus minus 0.3. And that is definitely that's definitely true. I would have been okay if it had been a sigma or two away, but this is okay. This is a good result. So
we can reduce this uncertainty by taking the uncertainty on the 7 also, just like 28. So because it's uncertain, you see. So if you sum 21 and 27, we should take the uncertainties on both.
No. The magic, we don't really suffer. The approach that we took is we decided 28 is a given. So that's and the only question that is related to, that would increase that certainly by the way, the only thing that relates to the result is whether they're in or out amongst the 28 that made it into the box, whether they're inside or outside the circle. So we say, our approach was saying that 28 has no uncertainty. It's only for the question of what value we get out, the only thing that matters is the uncertainty is whether it goes to one or the other category. That gives actually a smaller error, so we were not super conservative here. So the binomial errors tend to be smaller than what you were thinking would have effectively been a kind of Poisson error, and that would have sort of inflated the uncertainty in this case. All right. Are there any questions regarding this? Except that you all really need a coffee or tea or something like that now. Well, thanks for playing along with this one. I like it because it got us back to all these uncertainties and probability distributions that we discussed earlier. And I think really this is it. The last thing is various resources that you can choose to use or ignore as you wish, and that includes the problem sheet that I mentioned with solutions now, much easier with the solutions than without. The Monte Carlo simulation we just did as a Jupyter notebook in exactly the same way, with some question. So it's not complete. This will compile and you have to do something. But if you can't be bothered with this, here's also the solved version of it. And then the chi-square fit. The chi-square fit, there I encourage you really to look at it before looking at the solution, because here you'll find that the fit is biased, and it's nice to speculate why the fit, as I've given it to you there, is actually biased. Have a look at it if you want, and then if you get stuck or want to check your answers and see the solved version. So thank you all very much for playing along so nicely, and for being a brilliant participating audience. It was great fun.
Great, thank you, Professor Jonas Rademacker. We are really grateful to you. I mean, this was really interactive, wonderful. I like it. You all like it. I know it. Questions, comments, anything that you would like to ask? Coffee.
Yes. Sorry for running so badly. I had illusions of actually making it about 40 minutes earlier than now, so I don't know.
What do you expect the value of chi-square if we are using bin data?
The same thing. The value of chi-square is actually only defined for bin data. So I expect the value of chi-square for bin data to be, on average, the number of bins I have minus the number of fit parameters that give me the wiggle room to adjust the function for a good fit, where the function describes the data. By the way, I mentioned regarding chi-square, I mentioned that the likelihood doesn't tell you anything about the quality of the fit. That's a shortcoming of the method, I would say. And one way of getting around it is to first do a likelihood fit, and then afterwards calculate the chi-square and see whether it's sensible. But that chi-square should be a bit bigger than the chi-square from the chi-square fit. By definition, no?
So another question would be, how do you differentiate MLM from the least or the chi-square fit? So he already answered it, that when you have a Gaussian underlying, so both methods, they are the same on the average. Let's thank our speaker teacher once again. Thank you, Professor Paul. This was really great. And this was his last lecture. He would be leaving by tomorrow early morning. And of course, we're going to miss him. Yeah. Of course. But don't worry. We will call him by next year again if he is willing to come.
Well, thanks a lot for inviting me. I had a great time. I really enjoyed the school. I think it's a brilliant school. I very much like the atmosphere you managed to create and the intellectual atmosphere that's here, and the idea of participation and discussion in the evenings, and a really nice lectures through the day, apart from this one. But thank you.
Thanks again. That's it. Thank you guys. See you all, and we thank Professor Jonas Rademacker once again for being with us. And we wish him very good luck for his travel back home. Thank you.
Thank you.
And see you. Bye-bye.
Bye-bye. I'll work on my timing.